In this video, we're going to keep approximating limits, but instead of thinking about things graphically, we're going to move towards a numerical approximation of these limits. After this, we'll move on to how to actually evaluate limits, but for now, we're just going to focus on these approximations. So first, what we'll do is we'll remind ourselves of how we actually approximated limits by looking at the graphs. Then we're going to convert that process to something that we can use for numerical representations of our functions. And then after that, we'll take a look at a couple of examples. So, as a quick recap, how did we actually approximate those limits graphically? You might remember that we had a couple of different pictures that we were looking at. Our beginning definition of limits, we were thinking about left-sided limits and right-sided limits. We need those things to match up for our two-sided limit to actually exist. So the process in these pictures is that we think of x values that were on the left of, in this case, 3, it looks like. So we're looking at like an x value of 2, an x value of 2.5, and bigger and bigger and bigger as we approach 3. And we just tried to see what the pattern of y values was. What did it look like these y values were approaching as we moved to the left on this graph? And in this case, it looks like our left-sided limit was -2. Over in this picture, we have the exact same thing, but notice the x values that we're looking at are a bit bigger than 3. And so we're trying to see, again, what do our y values approach as x is close to 3, but a little bit bigger than 3. And then we kind of summarize this with this last picture where we just look at this little bar here, which represents the x values that are close to 3 on either side, and we're just looking at these kind of highlighted y values. Where are they? It looks like if we trace this back over to our axis, they're pretty close to -2. So again, lots of visual evidence that the limit as x approaches 3 of this function is -2. So what we're going to do is we're going to translate this technique to something that we can use with a numerical representation of our function. So here's our setup. We're going to numerically approximate this limit, and we're going to think about that representation of our function, which maybe doesn't make a lot of sense until we see what it is. It's just a table of values. This is something that we've seen since the very first time we really learned about functions, probably. One of our first representations of a function was just this table of values where you have these inputs, x, and corresponding outputs, y. So what we're going to do is we're going to pretend that we've got some function f of x that maybe we know what the function rule is. Maybe we only have some specific points. Either way, we're going to approximate this following limit. The limit as x approaches -3 of our function f of x. So here are the points that we have. You'll notice conveniently, we're given a lot of points with x values close to -3. So you can see on our left-sided limit, we have all these x values that are close to 3 but less than -3. And on our right-sided limit, we have all these x values that are close to -3, but bigger than -3. And for each of these x values, we have corresponding y values. So for our left-sided limit, we can follow our y values this way and numerically try and guess what they're approaching. It looks like in this case, as we approach -3 on the left for this function, our y values are probably getting close to something like 10. And here we have the same kind of thing. We can follow our y values from the right and see what they're doing. And it looks like we've got some good evidence that this right-sided limit is also 10. These y values are getting really, really close to something around 10. And so we probably have a good guess of what this limit is, right? Our two-sided limit is probably 10. Now, this is an estimation. It's an approximation. So we can't really say without a doubt that it is 10, but that's a pretty good guess. All right, so again, we are using best guess here. It could be that this limit actually was something like 10.000000479 whatever. We don't actually really know that this limit is actually 10, but it's a really good guess. All right, so maybe we don't just have the actual function values. Maybe we have a function rule instead. Maybe we're given the actual rule for the function, like something like this. Here, we've got some piecewise defined function for g, and we want to look at a limit as x approaches 2. So what we're going to do is the exact same thing. We're going to split this up, and we're going to look at a left-sided limit here, and we'll look at a right-sided limit. We're going to plug in some x values that we choose into this function and create our own table of values, just like we had earlier. So I'm just going to give us this same kind of pattern of x values and y values. We've got 1.5, 1.9, 1.99, 1.999, something like that. And we can see that these are our left-sided x values. They're slightly less than 2. And on the right-sided limit, we have the same kind of pattern, right? Very, very close to 2. As you move from the right to the left, we're getting closer and closer to 2. So what I want us to do is to just plug these values into our function. But first, what we'll notice is that with the left-sided limit, these x values are all less than 2. And so for our piecewise function, we're using x squared minus 1. So grab those x values, chuck them into your function, and see what kind of outputs you get. Similarly, over here, our right-sided limit, all of these x values are slightly bigger than 2. So we're looking at this piece of our piecewise function. So our function itself is now actually this square root of x plus 7. So pause the video, grab your calculator or whatever else you need, throw these values into these functions, and see if you can't figure out what's going on with this. All right, hopefully you have some actual function values. If not, pause this video, find them. You can do it. Pretend this is a real honest to goodness class where I'm making you pull out your calculator and plug these values in. All right, here's what they are, approximately. I rounded a bunch of these off because we get these nasty irrationals and stuff like that. But hopefully we can see a little bit about what's going on here, right? With our left-sided limit, we're going to follow these y values, and we're going to see what does it look like they're approaching. Well, it really looks like they're approaching 3. And again, with these right-sided values, we can follow our y values as x gets closer and closer to 2. And again, it looks like we're getting pretty close to 3. So I might make this claim that, hey, this limit as x approaches 2 of g of x, it's probably equal to 3. What I want us to notice is that, whoops, my function value itself is 1. Oops, g of 2 is equal to 1. That has nothing to do with our limit here, right? Because when we looked on the left side of this x value of 2 and on the right side of this x value of 2, our y values were getting really, really, really close to 3. Remember in the definition of the limit that we don't care about what happens when x is equal to 2. We just care about what happens when x is close to 2. So don't get too discouraged by grabbing onto this function value. We'll start to get trained into thinking that, like, okay, this function value has nothing to do with the value of the actual limit. All right, here's another example. Let's numerically approximate this limit. I'll let you go ahead and do that. But before we do that, I'll notice that this is kind of an annoying looking one. Let's go ahead and just use a quick little change of variables almost. So we're going to go ahead and let theta be x minus pi. And that means that as x approaches pi, we can see that theta is going to approach, x minus pi. Theta equals x minus pi. There we go. And so that's going to approach 0. When these two things are close to the same thing, the difference is going to be close to 0. So this limit really is just sine of theta over theta as theta approaches 0. So go ahead, grab some left-sided values for your left-sided values. Remember, you're thinking about theta values that are slightly less than 0. And for your right-sided values, we're going to think about theta values that are slightly greater than 0. This might be a good time to start noticing that we're going to be talking about these trig functions evaluated at angles that are always going to be represented in terms of radians. Now, in this case, it doesn't really matter because 0 radians is the same thing as 0 degrees, but go ahead and make sure that we're using radians for the rest of the course. Radian gang, stand up. So pause the video, find these values. I'm not going to actually do it. See if you can get close to a good idea of what these outputs, sine theta over theta, are getting close to. All right, hopefully you've got a pretty good idea here. Hopefully it looks like this limit as theta approaches 0 of sine theta over theta. Hopefully you've got a good guess that this is equal to 1. Now, again, this is just a good guess. This is a numerical approximation. It might be that this limit actually isn't 1. It's just something so close to it that we're not really getting enough detail in our approximations to notice the difference. So, again, remember, just an approximation. What we want to do now is start thinking about how we can move from these best guess approximations, and these best guesses are pretty good so far. Graphically and numerically, we're doing a good job of figuring out what's going on, or at least getting evidence of what's going on. And we want to move towards some more ironclad evaluations, actually getting the real honest-to-goodness value of these limits without having to do much guessing here. So in our next videos, we'll start going through some properties of limits where we can start getting at these evaluations.